So in this lecture, we will tackle the psychrometric processes. Many of the problems in processing moist air with various apparatus result in rather complex process lines on a psychrometric chart. Psychrometric processing with actual apparatus will be covered in later discussions. At this time, we will consider a number of fundamental problems which are independent of heat and or mass transfer rates in equipment. These problems will further illustrate some of the many uses for a psychrometric chart. All the processes considered here will be for steady flow conditions. The total or barometric pressure will be assumed constant throughout the process. This assumption is valid in almost all psychrometric processing problems, since even in actual apparatus, such as fin coils or spray chambers, the pressure drop is typically less than 1 inch of water. So first process here is the sensible heating or cooling of moist air. Okay. If it is added to moist air with no addition of moisture, then we speak of the process as one of sensible heating. Such process may occur if moist air is passed across the heated surface, such as a bundle of fin tubes, where a medium such as hot water or steam circulates inside the tubes. Sensible cooling is the reverse of sensible heating, and may occur if air is passed across a cool surface. To restrict the process to only sensible cooling, the surface temperature must be higher than the air dew point temperature. So, considering this figure here, so we're heating medium. And this Q from 1 to 2, so 0.1 here, and this is your 0.2. So have mass of your air 1, this the temperature 1, W1, and the enthalpy 1, and 0.2, you have here mass 2, temperature 2, this humidity ratio 0.2, and the enthalpy So when we draw its psychometric chart, so here that's our saturation curve. So here we have dry bulb temperature 1, we have this dry bulb temperature 2. Okay, and this is our constant humidity ratio, W1, this is equal to W2. So considering this is your point 1 here, point 1, that is your point 2. Okay, so this should be your enthalpy 1, and this should be your enthalpy 2. So this is our schematic device. As air passes to the heating medium, so this arrow is here. Eventually the air will the temperature of air will increase at point 2. So when consider the steady flow energy and material balance equation, so that is referring to the figure, this mass A 1 times enthalpy 1 plus Q1 to 1 to 2, this is mass 0.2 and enthalpy 2. So we have also the mass at 0.1 is equivalent to mass 0.2, and we have mass 0.1 times the W1 is equivalent to mass A2 W2. Thus, for sensible heating, you have this equation Q1 to 2 is equal to mass A, mass of air, times H2 minus H1. So since the humidity ratio remains constant, it is closely true that you can write this equation to This is M A (0.24) plus 0.45 W times T2 minus T1. This is applicable for constant humidity ratio. Okay, so go now to our example. So moist air enters a steam heating coil at 4 degrees Fahrenheit dry bulb temperature and 36 degree Fahrenheit thermodynamic wet bulb temperature at the rate of 2000 cubic feet per minute. Barometric pressure is 14.696 psia. The air leaves the coil at a dry bulb temperature of 140 degrees Fahrenheit. Determine the pound per hour of saturated steam at 220 degrees Fahrenheit required if the condensate leaves the coil at 200 Fahrenheit. Okay, so solution. So by looking at the psychrometric chart in English units, so you can have this W1 or this humidity ratio. Humidity ratio is equivalent to 0.0 by looking at the psychrometric chart. So we have this humidity ratio 1 equivalent to 0.00359 pound per pound of air. So have this H1 13.47 BTU per pound air, and we have specific volume 1. This is 12.66 feet cube per pound air. So by the figure also we can, or by the psychrometric chart, you can have T2 here is 140 Fahrenheit, and you have W2, this is 0.00359 00359. This is equivalent to W1. Okay, in H2, using this econometric chart again, you have this 37.7 BTU per pound mass of air. Okay, so also our MA, this is 2000 over 12.66 times 60. This is equal to 9479. Pound mass of air per hour. So therefore our Q1 to Q2 0.1 to 2, this is 9479 times this one 37.7 is the H2 minus H1, 13.47. So this is 229,676 BTU per hour. Okay, and using also this equation by another alternate solution by solving our heat here, we have this one, the 9479 times this 1.24 plus 0.45 times the W1 0 or the W, since it is equal humidity ratio. Okay, times this is 140 is the T2 minus the 40 here. So we have the same answer here, which is 229,013 BTU per hour. So that is approximately equal. Okay, so for the steam, by steam tables, we have this H, we have from steam tables we have the HG, this is 115 3.4 BTU per pound. This is for T is 220 degrees Fahrenheit. Okay, and we have this HF at 200 Fahrenheit. This is 168 0.10 BTU per pound at 200 Fahrenheit. So that's the rate of steam flow. The rate of steam flow. Here M S, we have 229,676. This is 115. 3.4 minus 168.1. So this, therefore this is 233.1 pound per hour. Okay.